Today we are going to discuss first isomorphism theorem of group theory, and this is very strong and powerful theorem of group theory. Without this theorem you will not be able to solve any kind of hard problem or tricky problem. You definitely need this theorem, and today I will show how nice actually this theorem is, and I will prove this theorem also. And what actually the statement says: if phi is an homomorphism from G to G dash, then G by kernel phi is isomorphic to phi of G. We have just given that phi is a homomorphism from G to G dash, and to show that G by kernel phi is isomorphic to image of phi. So what actually we have given, the phi is a homomorphism. That much, only this, that much we have given, that phi is a homomorphism. That means that if you take any element a comma b inside G, then phi of AB, this is equals to phi A and phi B. Okay, this is the definition of homomorphism, and you are I am assuming that you are already aware of what is quotient group, what is kernel of a group homomorphism, and yeah, etc., and basic fundamentals of group theory. Okay, so you have to show. Okay, let's define kernel phi. Kernel phi is all those elements in G inside G domain group such that if F is a homomorphism of, okay, phi of G, this cohesive identity of the group G dash, right? Okay, so this is kernel phi, and to show this theorem, if I can show that there exists a bijective group homomorphism between G by kernel phi to phi G, then I am done. Okay, so let's try to find a bijection and a group homomorphism, and define another map. Define psi G mod kernel phi to image of, okay, phi. So if I can show this actually gives you and I am defining that psi of what G by kernel phi is a quotient group and quotiented by kernel phi, and what are the elements of looks like of G mod kernel phi, that are looks like G kernel phi, right? And this is going on phi of G. Okay, so can you show this? If I can show that this is a bijection, homomorphism as well as a bijection, then I am done. So let's try to prove the homomorphism, whether it is a homomorphism or not. So homomorphism let's try to prove whether it is homomorphism or not. Okay, so we have given that the map psi, that is from G mod kernel phi to phi of G, right, and defined as phi of G kernel phi, which is equals to, this is phi of G. Okay, so whether is it a bijection? Let G1 comma kernel phi and G2 comma kernel phi are two member of G mod kernel phi, right? I have taken two element, okay, from G mod kernel phi, and let's operate them. Psi of G1 kernel phi, G2 kernel phi, okay, which is psi of there are two cosets, and under coset operation is defined as g1 g2 kernel phi, which is basically nothing but phi of g1 g2. Since phi is a homomorphism, then this is phi of g1 phi of g2, and phi of g1 is we can write it psi of g1 kernel phi, and this can be write it psi of g2 kernel phi, right? We are done. So psi of g1 kernel phi g2 kernel phi is same as this. So this is going to be a homomorphism. Now we are lefting out with the bijection. Okay, so this is a homomorphism. Homo. Okay, now we are only lefting out with whether it is 1 1 onto or not. 1 1 onto or not. Let's check the 1 1ness. Is it 1 1? What do you think? Is it 1 1? Okay, let's try to prove. And when we say a function is 1 1, a function is said to be 1 1 if their image, if we take two images are same, then we have to show that the elements are same, then we are done. Or if you can show the if you take the contrapositive of this, if you take two elements are not same, then their images should not be same, then we say that function is 1 1. Okay, so let's check the check the 1 1ness, and we are taking the first case or first test. Means that if I will take two images of psi, two images means this is image, and we will take two image two image means phi of g1 and phi of g2. I will take two images. So I will take let phi of g1 phi of g2 is to member of phi of g, and I will assume these two are same. I have to show the elements are actually same. Okay, so okay, so 1 1 is for let phi of g1, this is equals to phi of g2. This means that operate phi inverse g1. So phi inverse phi of g1 inverse phi of g1 is equals to phi of g1 that inverse into phi of g2. Okay, so this means that this will give you the identity, because inverse and operate with that particular with that element, it will give us the identity, and this is phi of g1 inverse phi of g2, right? Since phi is a homomorphism, then we can write down phi of g1 inverse g2, this is equals to identity. That means that g1 inverse g2 is a member of kernel phi. Okay, because phi is operating g1 phi is operating after g1 g2 inverse, after operating phi, it gives us identity. Okay, so it gives us identity. So this means that the g1 inverse g2 is a member of kernel phi, and we in a coset property, I think you are already aware that two cosets are same. I am just writing two coset AH and equals to BH. Two cosets are same if and only if AB inverse is in H. Okay, you're aware. So take A to be B inverse, G1 inverse, and B to be G1 G2 to be B inverse, right? So we are here, from here to here, you can definitely say that then G1 kernel phi is same as G2 kernel phi. It means that the elements are same. We have taken two images same, phi of g1 equals to phi of g2, and we are getting phi G1 kernel phi and G2 kernel phi are same. So this map is psi is 1 1. Okay, now we are only lifting out with onto portion, and you can and it is a very natural map, and you can it is clearly visible that this map is onto, because this map is G mod kernel phi, G kernel phi goes to phi of G. You take any element in the codomain, that means in phi G, I should be able to give you a function, an element inside G mod kernel phi, that phi of that the element that will give us that image. Okay, so let's try to prove formally, and although it is clearly visible, so ontoness, is it onto? Okay, so let the map I am writing G mod kernel phi, G mod kernel phi, G mod kernel phi to phi of G, right? So is this onto? Onto means this is, if this is phi of G and this is G mod kernel phi, if I give you any element here, you should be able to give me any pre-image over here, right? That means I am giving you one element over here. Let phi of G be any element, arbitrary element of phi of G, right? Then any arbitrary element, and you should be able to give me one element inside G mod kernel phi such that the phi of that image, that element, that will give us the phi of G. So let's check phi of G1, G dash is a member of. Okay, so can you give me an element inside G mod kernel phi or G by kernel phi such that psi of that image, that element, this give us phi of G dash? Yeah, I can give you. Take, if you have phi of G dash, and I will give you psi of G dash kernel phi. This is give a phi of G dash, right? So this map is onto. I am giving any element over here, and you should be able to give a pre-image over here. So G dash, the pre-image, G inverse kernel phi is a pre-image of G dash under the map psi. So this map is onto. So psi is onto also. Okay. So psi is a bijective group homomorphism. That means, so these two are isomorphic. G mod kernel phi is isomorphic to image of phi. Yeah, these two are isomorphic. Okay, so we proved this theorem and try to fill this theorem and try to apply this theorem in problems, and this is a very interesting theorem, and later on we will discuss the application of this theorem, where we can apply it and how nicely it works, and this kind of thing we'll see later. And today I've just given the proof of this theorem, and this might seems very difficult, but it is very easy, and you are already you have seen that how easily I did this theorem, and this is very easy, and it might seems very difficult. I know, even I also uh, thought like that in earlier whenever I studied, but this is very simple and interesting theorem. So later on we'll discuss the problem and the applications of this theorem. And okay, so this was for today, and thanks for watching.